Yes, good evening, Anirudh. Good evening. As usual, I am just waiting for some minutes. Then I will start my problem solving session. Today is the last day of my problem solving session of this course, Fundamentals and Application of Dielectric Ceramics. Okay, just waiting for a few minutes. Then I will start. And that file, just checking. Okay, everything is fine. Everything is fine. Just waiting for up to 6:05 p.m. and then I will start my discussion. Okay, it's already 6:05 and we can now start solving the questions. Uh, Before starting, as usual, I am just introducing myself. Amiya Mandal. I am a PMRF scholar of IIT Roorkee, and I am doing my PhD under the supervision of Professor K.L. Yadav. Here I am doing the PMRF teaching assistantship duty of a NPTEL course, Fundamentals and Applications of Dielectric Ceramics, of course code MM31. The course instructor is Professor Ashish Garg from IIT Kanpur. And today I am going to discuss about the week 8 assignment problems. That is assignment 8. There are as usual 15 problems and today is the last lecture, last problem solving session of mine. Okay, now we can start. Okay, we can now start from question number 1. And before going to the question, I'm just recapping all the things, all the I'm just recapping all the things that you have learned in week 8. You have learned in week 8 the domain walls. in a ferroelectric materials. Okay, you have learned about domain walls, its formation, when does it form, and how does it form, how many types of domain wall, what is the difference between domain wall and grain boundary and grains. Okay, in a ferroelectric material. In this lecture, you have in the previous lectures you have learned about ferroelectric material, pyroelectric material, piezoelectric materials, etc. And this is the extension of this discussion. First of all, domain wall, you have learned about this. Then domain structure and its properties of ferroelectric materials. Structure and property, how many structures, how we get different variants in for different crystal structures. Okay. Then you have learned about the phase diagrams and measurements of ferroelectric materials. Okay, how many types of phases are there in lead titanate, lead zirconium titanate? You already have learned in week 8 lectures. In this uh, discussion sessions also, I will discuss everything, okay, regarding the problems. Then you have learned also about the principles of measurements and applications of piezoelectric and pyroelectric materials. Okay, applications and measurements. How do the piezoelectric coefficients and piezoelectric properties are measured, and pyroelectric coefficients are measured from pyroelectric current. Okay, and at last, applications of piezoelectric and pyroelectric materials. Okay, so all these you have learned in week 8, and all the 15 questions are based on the on these informations what you have learned in week 8. Okay, let's now first start with question number 1. Question number 1, let's first, it's telling about the ferroelectric domains. It's about the ferroelectric domains. Okay, ferroelectric domain. So just read the question, and we are trying next to try to find out the question answer after knowing the information and its uh, concept about the ferroelectric domains, then try to find out the answer. Okay. The question is ferroelectric domains in a material represent what? Region of randomly oriented dipoles. You already know about the dipoles. Okay, you already know about the dipoles. Positive and negative charge, they are separated by a distance. Okay. So this is the dipole. So these types of dipole are presented as this. Okay. Okay. They are similar rotation, they are opposite orientation. Okay, so their orientations are randomly oriented dipoles inside the ferroelectric material. Regions of oriented dipole in a similar directions. So if dipoles are oriented at the similar direction in a region, it is represented as these types of notation. And they are oriented at anti-parallel way, just like antiferroelectric material, they are represented as this type of notations. Okay. Third option is region of randomly oriented dipoles, means dipoles where each dipole oriented randomly. Okay, each dipole oriented randomly at their net dipole moment turns to be 0. Okay. So, and the last option is region of oriented grains. Region of oriented grains. So, first of all, we try to find out that what dipole is and what dipole moment is. Okay, so this is a unit cell crystal structure of a material. This is a unit cell crystal structure of a material where positive and negative charges, that is the negative charge and that is positive charge. Positive and negative charges are situated at this orientation, and when we reorient the dipole means this turns out to be a dipole. They are separated at a small distance d. When we reorient this dipole, reorient means we shift we are shifting the negative dipole to the positive positions and positive charges to the negative positions, and looking the unit cell just like it. Okay. So this is the reorientation of dipole, means we are changing just the dipole arrangement. This is called the ferroelectric domains. You can see that uh, in a small portion of a material, for a particular region, these are some particular regions. You can see they are denoted in a black color dotted lines. Okay. In each particular domains, you can see that every dipoles are arranged in a similar direction. That is the main concept of the each dipole. Each dipoles are arranged in a similar direction. Here is also each dipoles are arranged in a similar direction. So at each region, this is called the region. Okay, a region of a material. So at each region, every dipoles are oriented at a specific direction. Okay, specific direction, and these are called the ferroelectric domains. Each each regions are called the ferroelectric domains, in where each dipoles are oriented at a similar directions. Okay. Now, when electric field is applied on a ferroelectric material, electric field is applied on a ferroelectric material, how polarization is changes? Polarization is changes in this manner, where you can see it is going into this state, that saturation state, then it is going into this state. You already know about this. Okay, so in this is a state 2. At this state 2, where you can see this is the monodomain state. Okay, monodomain state. Monodomain means every at each domain, at each region, every dipoles are arranged at a in a similar directions. So we can consider this whole region at a single region, in where every dipoles are arranged, and this is termed as a monodomain. Okay. So in this state where this is called the saturation polarization state, PS. Okay. And when we switch back the electric field direction, then the state 2, where in this state there are randomly oriented directions. Okay, randomly oriented directions in which polarization is 0. Okay. Similarly, at this point, this is a state 3, where there is a net polarization. Here, net polarization was in these directions. Here, net polarization was in the opposite direction. This is the changes of polarizations in the material. Okay. Okay. Uh, so, okay. So you have learned about the ferroelectric domains. Okay. So what will be the answer of the ferroelectric domains? Ferroelectric domains now, so region, this is the region of oriented dipoles in a similar direction. Okay, this is the region of oriented dipoles in a similar direction. Okay, okay, we can now move forward to the question number 2. Question number 2 is telling about that the depolarization field, depolarization field, this is a very important term here, means the field required to a fully polarized material is called the depolarization field. Okay. In a ferroelectric material is the result of number one, increased surface charge density at the surface of a polarized material. So when the depolarization field arrives, when we apply an electric field in a material, then the polarization occurs at the surfaces of the material. Okay. Surface charges occurs at the surface of the materials. Now, at this point, a depolarizing field inside the material, depolarizing field ED, has also been occurred to reduce the field applied field, to reduce the applied field. Okay. So when does it occur? This is the increased surface charge density. This is also true, and the monodomain formation after we have seen in a P loop formation in this area, monodomain was formed. Okay. Third option is highly aligned grain boundaries. Okay, highly aligned grain boundaries and high coercivity. No, that's not the true. We just try to find out what the depolarization field. Depolarization field is a ferroelectric material in a ferroelectric material arises when due to incomplete screening of the bound charges at the surfaces or the interfaces within the material. Okay, here is a breakdown of the factors that spontaneous polarization. Ferroelectric material exhibits spontaneous polarization. Okay. Then bound charges. That's a very important point. Bound charge. Okay. Spontaneous polarization leads to bound charges at the surfaces of the material. These bound charges generate an electric field inside the material. Okay. Next is incomplete screening. That's in a perfect conductor, the surface charges would be fully neutralized by the free charges from an external circuit or environment. Okay. So the main important point is the remaining uncompensated charges generate an internal electric field called depolarization field. Okay. So this is the concept. Incomplete screening. From incomplete screening, depolarization charges exist. Okay, and geometry and boundary conditions. The geometry of the ferroelectric materials, example given thin films, bulk, etc., and boundary conditions such as electrode, vacuum, dielectric surroundings influence the magnitude of depolarization field. For instance, thin films often exhibit strong depolarization field because of high surface to volume ratio. So these are the some concepts you must have to know all these concepts. And lastly, the depolarization field typically opposes the direction of the spontaneous polarization. Opposes the direction of the spontaneous polarization. This is a very important point. Can destabilize the ferroelectric state, leading to a domain formation or even separation of the polarization if it's strong. So first, try to uh, understand this concept given in this figure. This is collected from a research article from a very important journal, Nature Communication. You can see that this is a uh, semantic compensation of depolarization field. Uh, you can see that E depolarization is generated inside the material when surface charges are accumulated completely, and this surface charges creates depolarization field from positive to negative charges. Okay. So figure A is telling about the depolarization field in a freestanding ferroelectric material when there is no connection between these two. Okay. Now B, this figure B is a ferroelectric only capacitor with metal electrodes. If we apply the electrode plates here, and if we apply voltages there, then we get the E equal to 0. And in these cases, where ferroelectric capacitor with an additional series capacitor. This is a ferroelectric capacitor, and here additional series capacitor where external E dash is also applied. So E is proportional to depolarization field. Okay. So you have learned in lecture also that a domain is not to be a confused with grain boundaries. Okay, grain boundaries and domains are different things. Each grain boundaries can contain a large number of domains. Okay. Also, a domain consists a full domain consists of grain when there is a monodomain formation is occurred. Okay. So monodomain formation where each dipoles are oriented in a similar directions. Okay. Region of single orientation of polarization. This is called the monodomain. Now you have learned about the phase change from cubic to tetragonal when T is less than Tc, less than the Curie temperature. Paraelectric phases, from paraelectric phase, barium titanate transfers to a tetragonal phase where a small polarization is observed. But here, no polarization. This is a paraelectric state. Okay, cubic phase. You already have learned in the previous sections also. I have already discussed everything about phase transition at a particular temperature, how phases are transitions, phase transition occurs, and the phases, paraelectric and ferroelectric phases are transferred. Okay. So here mainly depolarizing field opposes the polarization. Okay. Just like if the depolarizing field occurs, then here in this direction polarization occur, and if depolarization field occurs, and this in this direction, in the opposite direction, this polarization due to occurs due to different orientation of charges. Okay, and in this region, in the middle of the region, barrier is formed. This is called the grain bound domain region. Okay, so if domain 1, this is called the domain 1. So it is just like the contrary or from originates from the depolarizing field and the polarization field. Okay, so the opposition force between the depolarization field and the polarization field occurs the domain. So it occurs from the increased surface energy and reduce the electrostatic energy. So now you can answer the question that depolarization field in a ferroelectric material is the result of which? Result of increased surface charge density at the surface of a polarized ferroelectric material. Okay, this is a region. Okay, next reason is monodomain formation in a ferroelectric material. So these two are correct, and the remaining two are not correct because highly aligned grain boundaries, no grain boundary contribution should be there. And high coercivity, no, there is no high coercivity. So we can move to the question number 3. Okay. Okay, just to wait for 1 minute, and I am just checking that everything is going well. Okay, everything is fine. Everything is fine. Okay. Now, question number 3, just read that what it's telling. What it's telling that domains in a ferroelectric material have the following attributes. Number one, domain size is governed by the competition between the energy of the depolarizing field and the domain wall energy. This is correct. Okay. And next is external electric field affects the domain size. Of course, there is a electric field involvement in the domain size affection. Okay. So this is also true. It relates to the grain size. No, domain is not relating to the grains. Okay, so it should not be correct. And its type is dependent on the crystal system. Of course, it's also correct. So we try to understand the concept behind this question. So ferroelectric domain. What ferroelectric domain is a alignment of dipoles in one of the polarized directions extend only over a region of a crystal structure. This is different regions in a crystal structure. Okay, already have learned regions of uniform. This so highlighted portion. Just look at the highlighted portion. This region of uniform polarization are called the domains. Okay, separated by a boundary called domain wall. Should not confuse it the domain walls with the grain boundary. This is very important point. Depending upon the grain size, can have one grain can have more than one or more domains. Okay. So this is a very important concept to remember. And the next is the type of domain walls that can occur in a ferroelectric crystal depend upon the crystal structure and symmetry of both paraelectric and ferroelectric phases. Okay. So it depends on crystal structure, and when it is a paraelectric phase means there is delta P, no polarization occurs. Different types of monodomain or domain formation, and when a ferroelectric phases occur means there is some types of polarization is present in there. So we cannot tell that there is a monodomain formation is occurs. A different region of a ferroelectric material, different domains are formed. Okay. For instance, the rhombohedral phase, just like PZT. Okay, in case of PZT, rhombohedral phases of PZT, the PZT, which is nothing but lead zirconate titanate. This is a mixture of lead zirconate and lead titanate. Mixture of lead zirconate and lead titanate. Okay, so it has a PS vector along PS vector along 111 direction and gives the 8 opposite direction spontaneously, and it has 180 degree, 71 degree, 109 degree domain walls. Okay, PZD 180 degree, 71 degree, and 109 degree domain walls. 109-degree domain walls. Okay. On the other hand, a tetragonal perovskite structure, just like lead titanate, okay, lead titanate has PS along 001 axis, and here domain walls are either 180 degree or 90 degree. That is also very important. So you must have to learn about the what tetragonal structure, and so in case of tetragonal structure 180 degree and 90 degree domain walls are formed, and in case of rhombohedral structure, in case of rhombohedral, uh, just like this occurs. So when we are going to cubic to tetragonal state, how 90 degree and 180 degree domains walls are forming, we are just discussing. So in when cubic to tetragonal phases are transformed, when P is less than Tc, T is less than Tc, then the polarization there is a change is delta P not equal to 0. Okay. So in these cases, in these tetragonal phases, uh, there is a PS displacement means the direction of the dipoles are along these directions, and in between them a 90-degree formation. 90-degree formation. 90-degree formation is generated. Okay. With their dipole arrangement with respect to the then dipole walls, domain walls. Okay. So uh, this forms the 90-degree domain wall, and when 180-degree domain walls are formed at each faces of this material, we can see that there are different charges, oppositely charges elements are formed, just like negative, positive, and this forms the orientation of the dipoles in this direction, and in the um, vicinity of these dipoles, there we can see that negative positive orientations are fully opposite, just like 180 degree. Then we can see that PS and ED, this is the depolarization field, creates 180 degree domain walls. Okay. So these are the schematic representation of 180 degree, 90 degree domain walls of a tetragonal perovskite, just like barium titanate. When barium titanate epsilon R versus T plot, you have seen that at a different temperature is 120 degree centigrade. This is cubic and this is tetragonal. Okay, this is cubic and tetragonal phase transition occurs. Now, the formation of the domains may also be result of mechanical constraints associated with the races created by the ferroelectric phase transition. Example given: cubic paraelectric phase to tetragonal paraelectric phase in lead titanate. Okay. But 180 and 90-degree phase domain minimize the energy associated with the depolarization field, but elastic energy is minimized by only the formation of 100. So these are the in which cases how what type of energy is minimized or not is discussed here. Now the question is, this is a very important concept you must have to learn. You must have to know that why there is a domain wall because of the minimizing the energy. Okay, how the driving force for the formation of the domain wall is the minimization of electrostatic energy. Minimization of electrostatic energy. Minimization of electrostatic energy. Okay, of the depolarization field due to the surface charges due to the polarization. Surface charges of polarization and the elastic associated with the mechanical constant. This is it. So, splitting up the materials into oppositely oriented domains or compensating the electrical charge via electrical conduction through the crystals. These are the two possible methods to minimize the electrostatic energy with the depolarization field associated with. So, what we have learned that tetragonal crystal occurs two domain structure directions, that is domain wall direction 180 degree and 90 degree. Rhombohedral of structure like so observed in PZD material shows 180 degree, 71 degree, 109 degree domain walls. So the origination of the domain wall is the competition between the depolarization field, that is the negative, and domain energy, that is the positive, will lead to the stable domain size, that is energetics. Stable domain size where electrostatic energy is minimum. Electrostatic energy is minimum. Okay, very, very important. That is. So that's are the concept. Okay. So you can see that what will be the answer. So the domains in a ferroelectric material have the following attributes. Domain size is governed by the competition between the energy of the depolarization field and domain wall energy. This is the answer. And external electric field affects the domain size. This is not true, and the remaining options are not true. So question number 4. Now move to the question number 4. It's telling about the domain size increases with what? Domain size. Now the factors, which factors the domain size controls. Okay, is controlled. Okay, so uh, we must have to learn about the domain wall energy. This is a very important factor. Um, how for changing in a for factor for changing the domain wall um, size or domain size. Okay, domain size. So for this, we have to must learn about the which the gives free energy, gives free energy. So how gives free energy is contributed in domain wall formation. So delta G is nothing but G minus G naught, which consists of these five different energies. What these five different energies is termed as UC, effect of applied electric field. So effect of applied electric field is always there in a domain wall energy, and bulk electrical and electrical elastic energy is also there. Depolarization energy is also there. Domain energy is also there. So here this domain energy you have must have to uh, aware about that UD is the energy related to the internal field setup in a crystal by the polarization and not compensated. So UD, this is the internal energy related to the internal field setup is expressed as epsilon naught A by D and Vp naught. So E star is a constant denoted by the dielectric constant. E is the dielectric thickness and P naught is the polarization at the center of the domain. And domain energy, UW, signified as termed as UW, it is expressed as, can be expressed in terms of the surface energy of the wall. That is a very important term. Surface energy of the wall. The surface energy during the formation of the domain wall is termed as the gamma. It's termed as the gamma. And domain width. Domain width. So domain wall energy and crystal volume. So domain wall energy is dependent on the surface, is directly proportional to the surface energy of the wall, and is directly proportional to the thickness or width. How thick it is, the domain energy is also getting larger, and it is inversely proportional to the volume. Okay. So to get a stable domain structure, this delta G has to be minimized. The delta G is minimized. Okay. For this, what have to do? We have to do UP and EX values same in each domain. They are constant, irrespective of the domain thickness, so independent of the domain size. Hence, where we have to treat UW, that is the domain energy, and UD, that is the internal and external energy field. So delta G is minimum in which direction? For this calculation, delta G with respect to delta D, with respect to delta D gives you 0 value. And here D, we can find out D means the thickness of the thickness or size of the wall. Okay. So D is nothing but the domain width. Domain width. So domain width, this is the domain width. Domain width is represented as root over of this gamma t by epsilon star p naught square. So we can see that domain width is directly proportional to the gamma, which is domain energy, wall energy. Means uh, domain width is increased when the domain wall energy is also increasing. Okay. Next is, it is inversely proportional to the P naught. It is inversely proportional to the P naught. Okay. Means how polarization is increasing. When polarization is increasing, reversely D is decreasing. Okay. So these two factors, otherwise epsilon star is also related to polarization also, and gamma is the thickness is nothing but the domain wall, so it is directly proportional. So mainly these two factors affects the domain width, and the question is also based on this concept that domain size increase with surface energy of the domain wall. This is the one option, and decrease in polarization. This is decrease in polarization. Okay. This is the two option, as gamma is varying with root over of D is varying with root over of gamma, and D is inversely varying with P naught. Okay, these two concepts mainly is applied here. Okay, now we are moving to the question number 5 that the tetragonal ferroelectric materials have ferroelectric domains of the type what? I have already discussed this question in question number 3 discussion. Okay. So for tetragonal ferroelectric materials have ferroelectric domains of type 90 degree. When when a ferroelectric material transforms from cubic to tetragonal phases, two types of domains are formed. One is 90-degree formation, means the each side by side domains are arranged in uh, 90-degree direction of the dipoles, and the opposite directions are formed due to the positive and negative charges orientations of opposite orientations and opposite formation of the dipoles, and due to which opposite orientations of polarizations are formed, and that's why the opposite polarization and opposite 180-degree domains are formed along the surface domain walls. So 90-degree or 180-degree are the true options. Okay. So we have just a cubic to tetragonal transition, phase transition. Okay. Here 90 degree 90-degree phase transitions has occurred due to the domain, and here 180-degree polarizations are occurring. 180-degree domain walls are occurring. Okay. So how domain walls are formed? Here you can see that in which if depolarization field is mainly uh, occurring in this field, then the direction of these two regions are along upward directions, and directions of these two regions are along downward directions. So in the middle of the range, in the middle directions, in this middle range, so they are directed upward, they are directed in upward directions, and they are directed to the middleward directions. And in between them, they are situated in the middle position. Okay, in the middle position they are situating in the middle positions, and they are immobile, and they are forming the domain wall width. Okay, so how 90-degree domain walls are formed? That's they are arranged inside, they are arranged like these directions, and they are arranged like these directions, means they are forming 90-degree. Okay, then the tetragonal formation where 90-degree and 180-degree walls. So domain walls would be determined by the crystal structure. Just like for lead zirconium titanium rhombohedral 90-degree, 109-degree, 71-degree. Okay, these types of formations are seen. Okay, there's 180-degree, 71-degree, and 109-degree. Okay, 180-degree, 180-degree, 71-degree, 190-degree for PZT along these directions. Okay, so now move to the question number 6. That is morphotropic phase boundary, MPB. Morphotropic phase boundary has following attributes. Okay, has following attributes. What are they? So morphotropic phase boundary. This is a phase boundary. This is a typical phase boundary in which morphotropy means two different types of phases are coexistent. What are the two different types of phases? The two different types of phases are rhombohedral and tetragonal phases are coexistent. It is mainly seen into the lead zirconium titanate material. Lead zirconium titanate. Okay. So wait, this morphotropic phase boundary is nothing but the coexistence of phases at the boundary. This is the coexistence of phases, mainly two phases at the transition temperature, Tc. Okay. So okay, let's now uh, clear our concept about some piezoelectric materials like barium titanate. Okay, so we already know about the piezoelectric materials of barium titanate, that piezoelectric which develops commercially for application of the generation of detection of the acoustic ultrasonic energy. Okay, now for in case of titanium substitute BZT or BZST increases transition temperature for tetragonal orthorhombic or orthorhombic. Uh, okay, so tetragonal to orthorhombic, for the tetragonal orthorhombic or orthorhombic rhomboidal transition enhances piezoelectric property. So in this case, piezoelectric properties is also is seen. Okay, now the most ideal example is lead zirconium titanate is one of the most used piezoelectric variety of application due to its excellent property and a high enough transition temperature. Because the transition temperature of lead zirconate is approximately about um, 800 degrees centigrade, and transition temperature of lead titanate is approximately about 250 degrees centigrade. So when we mix them, the transition temperature nearly lies about 400 to 500 degrees centigrade. Okay. So um, it has a perovskite structure, B site randomly occupied by either titanium or zirconium. So PZT is nothing but the for 53 or 47 percentage of lead zirconate or lead titanate. Okay, lead titanate, and where the B site AbO3 structure, B side is mainly occupied by the titanium and zirconium. Okay, B side is mainly occupied by titanium and zirconium. So this is a phase diagram of lead zirconium titanate, where lead zirconium titanate percentage and lead titanate percentage have been shown in their mole percentage. Okay, from 0 to this point and from 100 to this point. Okay, means approximately 47-53% is there, and there ferroelectric tetragonal phases is there in this region for lead titanate, and ferroelectric rhombohedral high temperature. So this region mainly coexistence of tetragonal T phase, rhombohedral R phase, T and R phase. This is called MPB, means morphotropic phase boundary. Morphotropic phase boundary. Okay, this is called morphotropic phase boundary. Okay, so and after a certain temperature, like above 500 to 800 degree temperature, it is showing about the cubic structure. So this is called the transition temperature, where ferroelectric to paraelectric. Ferroelectric means delta P not equal to 0. To paraelectric means delta P equal to 0. This transverse is called the transition temperature, where mainly cubic structure is formed. Okay. So ferroelectric rhombohedral phase below temperature. So this region mainly occupies the rhombohedral section, and this region mainly occupies by the tetragonal section, and in between them the morphotropic phase boundary has been formed. So as I have told about the 50-50 percentage of zirconium and titanium gives excellent property, that's like morphotropic phase boundary, hence coexistence, and materials will cool easily. So this property um, mainly increases the piezoelectric property. Piezoelectric property B33 value is much increased. Okay, B33 value is increased. Okay, so based on this concept, you can now answer the question that the morphotopic phase boundary has following attributes. It's a sharp boundary and crystal structure changes abruptly across its. It shows coexistence of rhombohedral tetragonal phases of ferroelectric material in the phase diagram. Morphotypic phase boundary composition of a ceramic show maximization of the piezoelectric property. This is very important. Okay, so morphotrophic phase boundary has following attributes that it shows the coexistence of rhombohedral tetragonal phase and morphotropic conditions. Okay, so um, I'm just checking that everything are fine or not. So I am just checking. If you have any problem, if you have any question, you can ask from this rhombohedral tetragonal morphotropic phase boundary. Okay. In the message section, you can ask any question. You can ask any question. Is there any question, Niruddha? Okay, please repeat this question, sir. Okay. So you can see that the morphotrophic phase, you can see the just look at this figure. Just look at this figure. Just look at this figure. You can see that um, just look at this figure. You can see that. Just look at this figure. You can see that there is a phase transition. Okay, there is a this region mainly contributes about the rhombohedral phases, mainly about rhombohedral phase, and this is the ferroelectric tetragonal phase. This is the ferroelectric tetragonal phase. So in between them, this mainly lead zirconium titanate mainly follows rhombohedral phase, and lead titanate mainly are related with this. So in between them, this region, okay, this region, what does it tell? It tells about the it tells about the morphotropic phase boundary. That is morphotropic phase boundary MPB. Two phases are coexisted at this region in the temperature of between 300 to 500 degrees centigrade. Okay, Kelvin. And above this, it's going to the cubic structure. Okay, okay. Is it okay? Have you understand this? Have you understand this? Please tell. Yeah. Yes. Thank you. Okay, next we are going to the next section. Next question, that question number seven. Question number seven is telling about what happens across a domain wall. Across a domain wall, what happens? Just read the four options. That crystal orientation changes. The orientation do not change. Okay. Direction of polarization changes. That is the answer. Crystal symmetry, no. Crystal symmetry do not change. Magnitude of the polarization changes. No. Magnitude of the polarization is same. So across the domain wall, what do you change? Across the domain wall, only polarization will change. Why orientation will change? Orientation means total orientation of a domain. Domain. It's not related to the domain wall. Okay, so across a domain wall, the direction of polarization only changes. Direction of polarization only changes. This is a characteristic feature of domain walls in a ferroelectric and magnetic materials, where orientation of polarization in ferroelectrics or magnetization in magnetic materials changes across the wall, while the crystal structure typically remains the same. So hence the correct answer is the direction of polarization. Okay, let's break down each other options. We try to find out the what other options tells and why they are incorrect. Okay, so okay, Dipanshu has been joined, and crystal orientation changes. This option refers to the change in the orientation of the crystal lattice. So Uh, orientation of the crystal lattice is not the structure, mainly due to the crystal structure generally remains the same. Crystal orientation changes are more relevant to the grain boundaries rather than crystal. So crystal orientation mainly grain, it relates to the grain boundary. Okay, relates to the grain boundary. Okay, not the other things. And next option is this is the correct option. This is the correct option. So this is not the correct option. Okay. This is the correct option in which the ferroelectric materials, the polarization refers to the alignment of dipoles, electrical dipoles, the alignment of electrical dipoles. So what across the domain one, what we will find the direction of this polarization changes. The direction of polarization in the changes along the along this only directions of polarization is changed. Okay, only the directions of polarization is changed. Only the directions of polarization is changed. Okay, okay. So, and third option is not also correct. Crystal symmetry do not change. Actually, the changes in the crystal symmetry more likely occur at the phase boundary. Okay, crystal symmetry. So, where transition from one crystal to another, just like cubic to tetragonal transition, in epsilon r versus t, we can see it barium titanate at 120 degrees centigrade from cubic to tetragonal. At this transition temperature Tc, it is transferring from cubic to tetragonal. Okay. So this is crystal symmetry changes at transition temperature, not at the domain wall boundary. And magnitude of polarization, no, magnitude is not changed. At this boundary, magnitudes are same. Magnitude are same. Here also magnitude do not vary. Magnitude is do not change. Okay, non-zero magnitude, but they do not change. So delta P is not equal to zero. Okay, in this, so delta P is not equal to zero. So in summary, that crystal structure orientation, it's mainly the grain boundary, direction of polarization change for domain, and it do not as a magnitude of the unlikely domain ones, it remains constant, and in fact that magnitude usually remains same, only the direction changes. You can see this here how metals, how dielectric for a dielectric material, how domains are varying. That when we measure the P loop, we apply the metals electrodes at each surfaces of the dielectric material. That is the metal. Okay, and the polarization of generates after we apply the um, this is the varied AC field, AC field. Okay, and we can see there are different positions of PE loop, different positions of PE loop, where at this point monodomains forms mean P plus or P saturations are equal. At this point, these types of, and when we increase the polarization value, this domains gets increased from there, and the orientation of the polarization is also changed at different positions. Suppose at these positions the orientations are in these directions, and at these positions the orientations are like these directions in opposite direction. If these are in directions and they are in opposite directions, so monodomains are formed in these two directions, in these two regions, monodomains are formed. So in these two regions, and at the middle region, means at these regions, at these two regions at these two regions, delta P equal to 0, means two oppositely polarizations are oriented at the same directions. Okay, just like it. At this position, you can see two dipoles are oriented at the similar directions, and at this position, monodomains are formed, and at these positions, there is a delta P variation, not equal to 0, delta P occurs. Okay, so based on this concept, you can now answer the question that what happens across a domain wall Crystal directions of the polarization changes only. Directions of polarization changes only. Okay, before going, just read the question number 6. Just read the question number 8. Okay, read the question number 8. I'm doing this the full screen. Okay, question number 8 is telling about the lead. The PZT is material which has following attributes. Okay, PZT, what PZT is, and mm. So PZT, what PZT is? PZT is nothing but lead, zirconium, and titanium 0.5. Okay, so PZT, you can see the, if you observe the crystal structure very carefully, that you can see there that you can see that this is the lead zirconium titanate structure, where it is a unit cell structure. This is a unit cell structure. Unit cell structure. This is a cubic structure. This is a cubic structure where A, B, C are same, in which temperature T greater than Tc, where this central position of titanium and zirconium, this titanium and zirconium central position, this is situated at a central position. But when it gets shifted, it so this central position gets shifted to the, so this shifting of titanium position generates polarization, accumulates charges at its surfaces, and it generates a polarization. Okay, it generates a polarization due to the shifting of this position of titanium or zirconium, shifting of this position of titanium and zirconium, at which temperature the temperature is T less than. So here cubic structure gets transformed into the um, tetragonal structure. Tetragonal structure. So what lead zirconium titanate is? Lead zirconium titanate is nothing but a solid solution. It's a solid solution of lead titanate and lead zirconium titanate. Very famous, very famous material discovered by Sirane and Swagacian Tikisi, 1951. Here, one main important property of lead zirconium titanate, which it show is morphotropic phase boundary. Okay, morphotropic phase boundary between tetragonal and rhombohedral phases exist around lead zirconium titanate and lead titanate composition. Okay, rather later lead zirconium titanate, we can note the maximization of piezoelectric performance is obtained around the morphotropic phase boundary composition for pure PZT solid solution system. This is why PZTs share majority of the industrial applications at present. And this is the source from where I have collected all these figures and informations. You can see that where morphotropic phase boundary is going to lead zirconium titanate, lead titanate. This mainly promotes about the tetragonal phase. This mainly promotes about the rhombohedral phase, and at their boundary between them, this mainly occurs at 50-50 percentage, at 50-50 percentage. nearly 50% by 50% of lead titanate and 50% of lead zirconium titanate, lead zirconate. And above the temperature, this is the boundary where we can see the Curie temperature occurs. Okay. So based on this, we can see that D33 value, this is nothing but Coulomb per Newton value, charge per unit force. This is nothing but the piezo coefficient. Okay, so this piezo coefficient is also high at this percentage. So piezoelectric constant is also high at this percentage. Okay, means this is a 50-50%, 50 at this 50 percentage. Okay, so this is also the cubic and rhombohedral phase and tetragonal phase. This is the R phase. This is the T phase, and their morphotropic phase boundary. This is the morphotropic phase boundary. This is the MPB morphotropic phase boundary. Okay. So rhombohedral and tetragonal phases are coexisted. Okay. So these are the concepts of this question that PZT material, which has the following attributes, that it's a solid solution of lead zirconate and lead titanate. Number one, it exhibit morphotropic phase boundary. This so high piezoelectric coefficient, or so these three options are correct. Fourth option is not correct. It's orthorhombic structure. No, it mainly shows rhombohedral structure, tetragonal structure, and cubic structure. Okay, that is rhombohedral. It mainly shows rhombohedral, tetragonal, and cubic structure. Okay, three phases are observed in lead zirconium titanate, not orthorhombic. Orthorhombic mainly observed in barium titanate. Barium titanate at um, minus 90 degree to 5 degree centigrade. Okay, so um, we can move now forward to the question number 9, that when heated from very low temperatures, from 150 degrees centigrade, okay, from 100 very 50 degrees centigrade, barium titanate exhibits following attributes. So in the previous assignments also, I have solved a question based on this barium titanate and its different phase transitions and different phases of different epsilon r versus t. Here, 150 degrees centigrade, 0 degree centigrade, 120 degrees centigrade. Here is also a phase transition occurs. Here also a phase transition occurs. Here also a phase transition occurs. This is here you can see the cubic phase. Here you can see tetragonal phase. Here you can see rhombohedral phase. Okay, so these types of phases are occur, and here you can also see about here you can see orthorhombic phase, and here you can see rhombohedral phase. So R2, R2, O2, P2, C. These four phases are observed at different temperatures. So this is the main following attributes of due to the structural change. So structural change and ferroelectricity in barium titanate. This is a perovskite structure of a Orpheus structure. A central titanium atom. This is the titanium atom. This is the titanium atom. Position of titanium atom. Position of titanium atom. Titanium 4 plus. Okay, 4 plus atom. How it gets shifted? How it gets shifted to these two directions, depending on temperature and their positions. Due to their shifting, it forms different crystal structure at different temperatures. Okay, so it mainly forms tetragonal PiO6 minus this is uh, this is called the uh, octahedral octahedral formation. Okay. Corresponding A are situated at each corners of. I already have told it a very first lectures where I discussed about unit cells and their orientations at different orientations. So this is the crystal structure of barium titanate. For cubic structure formation where A equal to B equal to C, and for non-cubic structure A not equal, there is a tetragonal structure due to the formation of this charge separation with temperature. So at different temperature, 120 degrees centigrade, cubic formation of barium titanate occurs due to paraelectric phases. Oxygen ions around titanium ions has regular octahedral and has a center of symmetry. Its TiO dipole moments allow cancels each other, and this paraelectric state. And below 120 degrees centigrade, non-centrosymmetric tetragonal phases occurs at 001 direction. Unilateral displacement of the positive titanium changes ion against surrounding. So displacement of ions creates permanent dipoles. That's why delta P not equal to 0. Oh, okay. So in along this plane, you can see that each directions this titanium octahedra cancels out that itself cancels out. But for tetragonal phase, for this is for cubic phase, and for tetragonal phase, you can see there is a clear shifting. Clear shifting of phases means delta P is not equal to 0 here. Delta P is not equal to 0, and that's why tetragonal phases occur where A equal to B and not equal to C. Because the distortion octahedra are coupled together in ferroelectric form, this is a very spontaneous polarization, just like 25 microcoulomb per centimeter. Okay. So barium titanate shows different structures at 5 degrees centigrade, orthorhombic O structure, less than 90 degrees centigrade, rhombohedral R structure. Okay, rhombohedral R structure as a result of symmetry, and tetragonal symmetry is also observed. So this is the main diagram of barium titanate. You can see that this is the main diagram. That there is there, you can see at this region rhombohedral structure is observed. At this region tetragonal structure is observed. At this orthorhombic structure, this is rhombohedral structure. This is orthorhombic structure. This is tetragonal structure, and the corresponding okay, space group are R3m, AMM2, and P4m, and PM3m. That's the cubic structure at greater than 100 degree. So TC is 120 degree, 5 degree, and minus 90 degree. Three TCs are found, and they are corresponding dielectric constant is also increasing. Okay. So now we can move forward to the options that first it shows three phase transitions. Phase above 120 degrees cubic, monoclinic do not, and it is a pyroelectric material. All ferroelectric materials are pyroelectric and piezoelectric materials. We know about the concepts. So three options are correct. This is not correct. Monoclinic is not correct. So we can now move forward to question number 10. That ferroelectric hysteresis loop measurement. That's hysteresis measurement. Hysteresis loop measurement From okay, so this hysteresis measurement, this hysteresis measurement, for this hysteresis measurement, which circuit is used? Shower tower circuit. Shower tower circuit is used. Device in metal insulator, metal architecture. We can also use it, and we can also use a voltage source. We also use a voltage source. So these three options are correct. Okay, so measurement of hysteresis loop is mainly done by shower tower circuit, uh, where a high frequency AC field. This is the high frequency AC field is applied on the crystal. This is the measuring crystal whose polarization versus electric field loop is to be measured, and a oscilloscope is there, and there this is called the reference capacitor. This is called the reference capacitor. Okay, so this is the schematic diagram of a shower tower circuit, by which we can um, in where we fix a C naught value approximately about few microfarad to few nanofarad range. Okay, few microfarad to nanofarad range. We fix them, and then we apply some constant voltage, like from some voltage like 1 kilovolt to some megavolt, some few voltage like 400 to 500 kilovolt, and there is constant resistance, that is a reference resistance is also there. Resistance is also there, approximately 10 kilo ohm. Okay, 10 kilo ohm. Yeah. And now there is a voltage source, not the current source, only the voltage source, not current source. Okay. So there is a difference between voltage and current source. This is the voltage source and this is the current source. Voltage source mainly are battery, galvanometer, single cell in an internal series resistance. So for a voltage source, it is a resistance is connected in series. A resistance is connected in series. Okay. And here, constant voltage, nearly approximately constant voltage, and a loss due to this resistances is occurred for a practical voltage source. So, and there is a current source where resistance is parallelly arranged, where the current versus voltage got source are these types of plots. Okay, and this is connected from this source. I have collected this data. Now, based on this examples, you can now answer the question that ferroelectric hysteresis measurement of a ferroelectric use shower tower circuit. Use shower tower circuit, and here device is metal insulator architecture, means here if the this is the dielectric material, we apply silver paste at two tops silver electrode. So metal insulator, metal formations is also this architecture is used to measure this the ferroelectric P loop and hysteresis loop. Okay, and the voltage source, as usually have told about the voltage source is also, this is the voltage source is also applied, not the current source, not the current source. So current source is wrong option. Okay, so next we can move forward to question number 11, that for making dielectric measurements, what should be the contact between the electrode and the ceramics? There is a, you can see how electrode and the ceramics are. So these are the conductive silver paste which have been pasted on the upper and the lower side of the dielectric material. This is the dielectric palette. This is the dielectric palette, and we measure it at LCR meter. So question is that what type of contact? What type of contact is there? What type of contact? Is it a Schottky? Is it a ohmic? Is it a so what type of? Mainly ohmic contacts are there, presents there. Mainly ohmic contacts are present there. So what ohmic contact and Schottky interface actually uh, tells us about, and how their um, contribution in the contact. So you can see there I have collected it from this source. You can see that for ohmic interface means there is an oxygen ion contribution vacancy, and you can see there is this zinc ion and gallium ion, and there is a free volume also. Okay. Uh, And after post annealing, you can see there is a formation of the oxygen ions have been separated in this layer, and oxygen vacancies are also shifted in these positions. That's why the free energy positions and their curve is also have been changed. So how why ohmic interface is there, and why not Schottky interface is there? Due to this barrier, you have to follow this barrier in case of Schottky interface. Okay, I am not going to explain all these details. Just I am telling brief discussions about Schottky contact. That Schottky contact is formed when a metal and a semiconductor comes into the mm, metal and semiconductor comes. But ohmic contact forms a metal semiconductor junction, allows current to pass easily in both direction. Minimum resistance gives, so no barrier. This is the very important point, that no significant barrier at the present. No significant barrier is present. So here no significant barrier is present. You can see no significant barrier is present. So easily they can transmit. Okay. Minimal resistance is also there, and no rectifications is there. Current to pass at the ohmic contact. But here the barrier present at the Schottky defect. There is a barrier leads to rectifying behavior, allowing current to flow easily in one direction. So that's the main difference of a barrier, and ohmic contact mainly follow the Ohm's law. That's why ohmic term has been introduced. And for rectifying contact is nothing but junction where current flows preferentially in one direction, much like in a diode. So rectified in so one directional current, one unidirectional current is there in diode. So it is not unidirectional. There we apply a AC voltage, and the current should flow in each directions. So ohmic contact is preferred. With large resistance, what does it signify? Like a sort has a large, it means there is a significant resistance. This should not be possible in a ohmic contact. So this is not, we do not require large resistance. Okay. This terms had a poor contact quality also. So do not interested in it. So as summary, you can see that Schottky contact. Okay, Schottky is barrier present here without barrier, and rectifying contact, it restricts current flow in one direction, and large series it reducing current flow. So these two we do not use for a contact in a dielectric material. For contact in a dielectric material, we only use the ohmic contact. We do not use Schottky and rectifying large series resistances. Okay, we are moving to question number 12. Just seeing that everything is going well or not. Okay, everything is fine. Everything is fine. Okay. Now, question number 12, it tells us about The indirect piezoelectric coefficient has the following attributes: that piezoelectric effect, we already know about the piezoelectric effect, a direct, mainly direct piezoelectric effect tells us about what? Charge created per unit force. So that's why its unit is Coulomb per Newton. Okay. And where D33 values are measured in piezoelectric effect, and converse piezoelectric effect nothing but application of electric field generates charge polarization. Okay. So that's the difference. And so a strain, that is strain versus field for converse piezoelectric effect, and 1 by meter per volt, that is volt per meter. Volt per meter is the unit, and that's why it turns out to be meter per volt, that is given here. Okay. So direct piezoelectric effect is nothing but polarization. Application of stress gives rise to the change in polarization. That's why polarization is nothing but sigma, and D is nothing but piezoelectric coefficient. Okay. When it and reverse is nothing but, that is the direct, where we apply sigma and generating P, apply sigma in opposite direction generating P also. Converse piezoelectric effect, applying field applying, and we are creating opposite charges. Yeah. Okay. So that's the major difference between direct and converse piezoelectric effect for basic force, pressure, vibration, acceleration sensor. Okay. So what is the question telling about? Indirect piezoelectric effect, where application of field generates the charges, means it relates string to electric field. Hmm. First option is telling about it relates charge generated to applied field. No, it mainly it tells about the direct piezo effect. This is indirect, and it has the unit of no. This is also not correct. It do not have. It has a unit of meter per volt, as I have told you that it has a unit of meter per volt. Strain by field 1 by volt per meter, that gives you meter per volt. So these two options are correct. Yes, A and C options are not correct. Move to the question number 13. Now, which of the following are the methods of measuring piezoelectric coefficients? So, methods of measuring piezoelectric coefficients. Okay, this is the main topic. You have learned different methods of measuring piezoelectric coefficients, and there how many different types of measurement. There are different four types of measurement, of direct measurements and indirect measurements also. Like cantilever shower tower circuit is mainly measurement of field. So this is not correct. Shower tower circuit is not correct. This is correct cantilever method, optical interferometry method. Okay, so these two are correct. Leakage is not correct. So these two are correct. We will discussing here that measurement of ferroelectric meter. This is so first of all we have to measure displacement of the material, and when electric field is applied, and a resonance. Okay, and the resonance method. This is called the resonance method. So one is resonance method. Resonance method. Okay, where characteristic frequency of the material upon the application of electric field is widely used for bulk ceramics. Okay, so here a simple example has been given, that how length has been changed from 6 inch to its 1 by 4 inch. Okay, diameter, and that's related say LCR circuit are applied for C naught. For a mechanical part is there. and you can see the coupling coefficient also there. And you can see we can measure also D33 value by this formula. But some direct techniques you have already learned in in the lecture classes, that first piezoelectric measurements for direct techniques are just by normal load, application of just normal load. Okay, in which we can measure up to 20 picocoulomb per Newton charges generated per unit force application. Per force application. That's so D33 just like charge generated per unit force. So Q by F. Okay. So next direct type of measurement is use of periodic periodic compression. Periodic compression. Um, 0.03 picocoulomb per Newton. That's reference, where you can see these types of measurement um, techniques has been used, that silicon and we paste metal at that, and that piezo metal is placed at this position, and there is a coupling liquid, as a liquid is used. Okay, and there's a metal rod, and it's steep, and here diameter problem is also there. The surface should also be touched at the piezoelectric material. Should always be touched at this materials, and piezo metal rod is also there. So this is the use of periodic compression, and the next, which is cantilever method. Cantilever is nothing but a beam which is to be bent, after the application of this Tekati lever, after the application, and in which method we can measure up to zero point 0.6 coulomb per meter square. Hmm. And the pneumatic pressure optical interferometry meter, where a laser has been used to lenses uh, in this electrode region, and operated to a sample, and it is recorded to this, and by which we can measure up to zero point 0.1 picocoulomb per Newton, um, the piezoelectricity coefficient. Beside this, we also have surface acoustic swab, bulk acoustic swab of some indirect methods. Okay. So you can see that for in this region, cantilever method is also used here, and optical interferometry, where laser beam is used, is by which we can use the measure the piezoelectric coefficient also. Okay, and okay, next only two questions are left there in this problem solving session. So just to read this question number 14, we have also left 25 minutes extra to complete this session. Okay, if you have any question, you can also ask. Okay, just read the question. The dynamic. This question telling about the pyroelectric measurement, how pyroelectricity is measured, pyroelectricity of a sample is measured. Okay. Okay, a dynamic pyroelectric measurement. Just read that dynamic pyroelectric measurements requires. So one is dynamic measurement. There is two types of measurement. One is dynamic. Next is static. Okay, dynamic and static. So this question is based on dynamic measurement of a pyroelectric material, pyroelectricity, where mainly pyroelectric current. By measuring the pyroelectric current, we can measure the pyroelectric um, constant. Okay, so this is the setup where we can measure, you can see this is the pyroelectric material. This this is a pyroelectric material where IP is the pyroelectric current is generated. Across pyroelectric material, resistance parallelly is connected and within a oven. After heating, pyroelectric mainly measures about the delta T versus change of T, change of charge after the applications of temperature. Okay, this del Q by del T is the pyroelectric coefficient. In this temperature change, some charges are generated. These charges forms current. So with the measurement of the current, we can find that this measurement of current we can and measurement of delta T, you can find the um, pyroelectric coefficient. So this is the output circuit where current amplifier and output signals are generated. This is the IM, and here is also a resistance is grounded with this. And so how pyroelectric coefficients are measured? That this is the pyroelectric coefficient, which is nothing but current by A into dt. Change of temperature, time dependent temperature. Okay, this is very important. You must have to know about this. How temperature is changing with time. And this is pyro IP. That's we have to measure. So IP is nothing but IM. We know about IM, RS, RA. So IP is measured from just measure the IM value from this current amplifier, and this RA value and RS value both are known. So after knowing these three values, you can measure IP. Just measure the area of this palette, and you can easily find the pyroelectric coefficient after applying all the values of IP, A, and DT, DP. Okay. So RS and RA is leakage resistance of the sample and input resistance of the amplifier. They are known value. You have to apply a certain resistance in the amplifier, and the leakage resistance is also measured by the instrument. Okay. So what pyroelectric measurement is uh, affected, how PE loop is affected with temperature. With temperature, we can see the temperature dependent PE. This is decreasing, means there is a difference between delta P. Delta P is varying. Delta P is varying. Okay, P is varying. Means delta P is changing. Okay, this is very important concept. P is changing. So this changing occurs mainly. We know that how P varies with temperature. How P varies with temperature. It goes down um, when at a particular temperature, that is the Curie temperature. So at a certain region, how polarization varies with temperature, dP del T, that gives you the pyroelectric coefficient. Pyroelectric coefficient. This is the measurement techniques of pyroelectric coefficient mainly. Okay. Mm. So we can now answer the question that, so dynamic pyroelectric measurement requires what? Dynamic pyroelectric measurement requires a pyroelectric current only. No leakage current is required, no dielectric constant is required, only measure the pyroelectric current. You can measure the pyroelectric coefficient. Okay. Next, the last question of this session and of this last session and the last question. This is a very easy question, just application based question, that the application of a pyroelectric material, in which cases the pyroelectric materials are applied. So gas lighter, acoustic sensors, non-volatile random access memory. There are four options that you can see. That gas lighter, this is correct. Acoustic sensor is correct. This is non-volatile is not correct. It is mainly if ferroelectric RAM, ferroelectric RAM measurement we can. Hmm. This is for ferroelectric, not for pyroelectric measurement. Ferroelectric RAMs are there. Okay. Random access memory, ferroelectric RAM. The switching behavior is observed around the PS plus minus PS. Okay, switching behavior is observed, and that's why it's non-volatile. Volatile should be there. Non-volatile means there is a switching of ferroelectric at PS means we can signify it as a plus one state or zero state, that is plus PS and minus PS. So that is the concept. You can easily find in any standard paper for of FRAM. So that's the three applications are um, um, can be true is true here for pyrotechnic materials application, that pyrotechnic sensors for do it pyroelectricity measurement of charges with the temperature difference. So there always a difference of temperature. So infrared radiation creates the temperature difference. Infrared radiation creates the temperature difference. That's why charges are generated. That's why pyroelectricity is going to important here. So infrared radiation is very kind where infrared cameras are used. Okay. So these are the some infrared imaging. Okay, you can see that how infrared radiation generates temperature. Here is the temperature generation from infrared radiation. Infrared radiation mainly generates temperature. That's why charges are generated. That's why pyroelectricity. How dog's eye are um, shows light, these types of lights due to generation of temperature, due to generation of charge, due to the involvement of temperature due to the infrared radiations. Okay. Okay, so process of image creation, how image creation is being processed in a thermogram. Here's a thermogram. It's called a thermogram. How temperature is increased and how they can be found. Okay, so this is the formation process of here object to lens and detector and signal processing. It's how and it goes to monitor. Then we can see the images found and how gaslighters are work. How gaslighters work. There are two opposite polarized at a single means. So when this two opposite piezoelectric materials are um, being connected at each opposite position, so that two plus plus are situated at the same interfaces, so that a spark is generated. Spark. This spark generates this spark is used in a gas lighter by following the piezoelectric behavior. Okay. Okay. So how piezoelectric sensors are, this is ultrasonic imaging also acoustic imaging, that just send the some acoustic or ultrasonic wave to any of the object, and when it gets reflected back and that detect if the detector detects these reflectance, then we can find the mm, observations or find the position of this any object by detecting this ultrasound or. Okay, so that's are only discussed here. So only piezoelectric sensors, detections of generations of sonar wave, detections of automatic engine. Thus, these are some. You can read all this application. Medical application, ultrasound waves are very important. Okay, in kidney stones, so kidney stones, in case of kidney stones, okay, it's also used. Hmm. Okay, so for infrared radiation, you can see that there is a coating in one side and other side remaining left. This is left. So, so this coating generates charge, and this is allowed. Infrared radiations are allowed in this radiation, but infrared radiations cannot pass forward to these directions. So a charge delta T is generated due to the generation of charges, plus and negative charges and positive charges are generated in the surface, and pulses is generated. Okay, that's why how it works for infrared radiation, and how gas detections works. Here is also infrared sources passes through a gas chamber, where in one side gas is allowed to pass, and in other side gas is allowed to out. And in this region, infrared is absorbed by the gas, and it is detected by the pyroelectric detector. So there at before there is a reference voltage is also going to calculated uh, to make a difference, and by observing this difference, a pyroelectric measurement has also been created. So you can now see that how gas lighter works in pyroelectric material, how acoustic sensors works, how infrared camera works. Okay, so all these are the applications purposes. Okay, so I have completed uh, all the questions, and if you have any questions, you can now ask. So, is there any question, Anirudh? Is there any question? Okay, there is no questions. So we can now leave the meeting. So this is my last lecture, last problem solving session. I am just checking I have done all the questions or not in this session. So question 2 is already done. Question 3 has already done. Question 4 is all done. 5 is okay. 7 is okay. 8 is also okay. 9 is also okay. 10 is also okay. 11 is also okay. 12 is also okay. 13 is also okay. 14 is also okay. 15 is also okay. So I have done every questions, and I have done every questions. Just checking. Okay. Okay. So uh, from July, from July 31 to September 17, I have conducted 8 problem solving sessions from assignment 1 to assignment 8. Today is the last uh, day. I am finishing here. I think I have tried my best to do the questions, to do the solve, and to clear the concepts of all the questions. And I think you all are satisfied with uh, my problem solving sessions. And so, what you have learned from assignments 1, where I have discussed about from assignment 1, you have learned about basics of crystal structure, basics of crystallography, arrangement, atoms, and crystal lattice. Okay, so and in assignment 2 also you have learned about Pauling's rules, ceramic materials, defect chemistry of non-stoichiometric crystals, and concentration effect of intrinsic impurity. In assignment 3, we have learned about intrinsic defects, some defect concentration, metal oxide intrinsic, Brouwer's diagram, introduction of dielectrics. Okay, and In week 4, you also learned about dielectric displacement, polarization mechanism, different dielectric polarizabilities, okay, and their frequency dependence of dielectrics. In week 5, you have learned about losses in dielectric materials, frequency dependence of dielectric constant, dipolar relaxation, Debye equations for dipolar relaxation, impedance spectroscopy, and in week 6, you also have learned about impedance spectroscopy, dielectric breakdowns, basics of nonlinear dielectric, piezoelectric effect, pyroelectric effect, different types of effect and their correlations, and thermodynamics of piezoelectric, pyroelectric. In week 7, you also learned about basics of ferroelectric material, basics of phase transitions of ferroelectric materials, thermodynamics of phase transitions, second order phase transition in ferroelectric material, first order phase transition. Okay. And in week 8, means in this week, today, you have also learned about domain wall formation, domain structure properties of ferroelectric material, phase transition, phase diagram, and measurements of ferroelectric materials, principles of measurements of applications of piezoelectric material, and the applications of piezoelectric piezoelectric materials. So, today is the last lecture, and I think I have um, tried my best uh, to solve every questions with clearing every concepts regarding this every week's problems and every week's lecture. So, thank you everyone. So, thank you Anirudh, thank you Dipanshu. Okay. So, uh, so thank you. See you soon. See you on our next session. If I will take any course for problem solving sessions. Okay, let's tata. Bye bye. Good night. See you soon. Okay. Okay, so we can now uh, finish this problem solving sessions and for this semester. And okay, thank you everyone.